Hello everyone, welcome to Probability and Statistics for Data Science. Today we're going to talk about confidence intervals for proportions and probabilities. This is a very important application of confidence intervals in practice. For example, if we want to estimate the fraction of people in New York that have COVID-19 from limited measurements, then it's critical to build a confidence interval to quantify our uncertainty about the estimate of this fraction. Similarly, if you're performing Monte Carlo simulations to estimate a probability, it is very important to have a confidence interval for that probability to know whether you have done enough Monte Carlo simulations to obtain an accurate estimate. Let's get to it. We're going to talk about confidence intervals for proportions and probabilities. The plan is to explain how to build those confidence intervals for these particular parameters, then explain how to apply this to Monte Carlo simulations, and finally talk about the limitations of the confidence interval framework. All right, so as a motivating example, let's imagine that we're in the middle of the COVID-19 pandemic and we want to estimate the prevalence in New York, but we don't have a lot of tests. We cannot test the whole population. Okay, prevalence is just the fraction of people in New York that have COVID-19. We're after estimating a population parameter, which is the population proportion of people that have COVID-19. Here we're going to assume that 5% of New Yorkers have COVID-19, and we want to estimate that value. So here I'm showing you a histogram of the population. Realize that this is logarithmic because otherwise I cannot put the population and our samples in the same histogram. So the white histogram just shows that This is the histogram of the people in the population that are negative and positive. The ones that have COVID-19 are 5%. I do not have access to that because I cannot test the whole population. Instead, I sample 1,000 people. I select 1,000 people at random from the population. And this gives me this mini histogram here. And that's going to, like, the fraction of those people that test positive, we're assuming that the tests all work, that's going to be my estimate of the prevalence of COVID-19 in New York City. In this case, I get an estimate of 5.5%, so not so bad. What is critical to understand here is that even though this fraction is not going to change, there's 5% of people that have COVID-19, that's it. If I repeat my measurement process, I am going to get a different estimate because I'm going to select 1,000 other people. Here, for example, my estimate is instead 4.9%. I repeat, I take 1,000 other people, boom, I get a different estimate. To drive this point home, let's take a look at the sample proportions of 10,000 repetitions of this procedure, and we see that they are centered around the true prevalence, which is 0.05, but there is a certain variance, there is uncertainty in our estimate. Our goal, if we're trying to do this in practice, is to characterize the probabilistic behavior of the sample proportion in order to quantify this uncertainty. A confidence interval allows us to do this by, instead of reporting just our estimate of the prevalence, reporting a range of values that is going to contain the true prevalence with high probability, 95%. So let's take a look at our mathematical model of this situation. We have this data that indicate whether each person in the population, so big N in the case of New York City is 8.8 million people. AI indicates whether the ith person has COVID-19 or not. And as I say here, and what we do is we take random samples. We select in our example, 1,000 people. So little n would be 1,000 people completely at random from the population. Each of these guys is equal to 1 if that particular person has COVID-19 or 0 otherwise. And there's the same probability of choosing any individual person at each point. And the samples are all independent. It's not that we're going to a neighborhood and just picking 1,000 people from that neighborhood, for example. In that case, we have seen in previous videos that the sample proportion, which is just the sample mean of our measurements, which makes a lot of sense, right? We're summing how many ones we see and we divide by the number of measurements. Okay, this is not a controversial statement, right? In that case, we can apply the confidence interval for the population mean that we applied, that we built in the previous video on confidence intervals. let's remind ourselves, if we have some independent random variables with mean mu and variance sigma squared, and we take their sample mean, their average, then the mean is going to be equal to mu, in our case, the population proportion, if we're applying this result to the sample proportion, which is what we want to do. And the variance scales like 1 over n times the population variance, okay? So this gives us a confidence interval, assuming that the random variables tend to a Gaussian distribution, which happens because of the central limit theorem. It gives us a confidence interval of this form, which we derived in the previous video. This constant just depends on the actual shape of the Gaussian distribution for zero mean and standard deviation, and typically for a value of 1 minus alpha is just going to be fixed. So here, let's say that we're interested in a 0.95 confidence interval. We obtain this confidence interval for these independent random variables with that mean and variance. And now we're going to apply this to a sample proportion. Okay, so hopefully that makes sense. There's a longer justification of why this is a confidence interval in the previous video on confidence intervals. Okay, so now let's apply this result on confidence intervals to our particular case. Realize that in our case, what we have is Bernoulli random variables indicating whether the person has COVID-19 or not. The reason why I'm writing this in a bit more of a general way is so that we can directly apply this to probabilities when we talk about Monte Carlo estimation. Okay, and this parameter theta is just the population, the probability that someone has COVID-19, which in our case is just the population proportion, right? Because when we pick someone at random, the probability that they have COVID-19 is exactly 5% in our example. So we're interested in this sample proportion, which is the average of these Bernoulli random variables. What is their average? It's just the parameter theta, right? This follows from linearity of expectation. If we look at the variance, we're going to get the population variance, okay, with which is equal to theta times 1 minus theta, because we have Bernoulli random variables, divided by n. Okay, I'm calling that the population variance, but hopefully it makes sense what I mean. Okay, and this follows from independence, okay, and then linearity of expectation. And now, by the central limit theorem, we can apply the previous result where things are approximately Gaussian, and we have this confidence interval, which depends on the parameter. We already encountered this issue when we talked about confidence intervals for the population mean, where there we had the population variance. That was very annoying in the case of the population mean, because the population variance potentially could be extremely large, right? Which would really affect the confidence interval. However, in this case, that's not completely the case, because theta is between 0 and 1. So this quantity can actually be controlled for any theta between 0 and 1 quite easily. This will give us a more conservative confidence interval than if we actually plugged in the actual parameter there. But we cannot plug in the actual parameter, because if we knew it, we would just, what's the point of estimating it? Remember that here we're trying to estimate this parameter of the Bernoulli random variables. In our example, that parameter corresponds to the prevalence of COVID-19 in New York City. Okay, so let's think for a moment about how we're going to bound this term. Well, this is a function of theta. We can take its derivatives to see how it looks. When we take the first derivative, it's just 1 minus 2 theta. When we take the second derivative, it's minus 2. That means that the function looks like that. So it arrives at a certain maximum where this derivative is equal to 0. That's exactly at theta equals to 1/2, where the value of the function is 0.25, right? Because it's 1/2 times 1/2. So we can replace theta times 1 minus theta by 0.25, and this gives us a more conservative confidence interval, which is maybe not great, because the confidence interval is going to be wider than it should, but we're guaranteed that it's going to contain the parameter of interest, the population proportion, or the probability that we want to estimate, as long as the Gaussian assumption holds. Okay, so that is bounded, and now we can just plug in 0.5 here, because 0.5 is the square root of 0.25. And if in particular we're interested in 0.95 confidence intervals, this gives us a confidence interval that is going to contain the parameter with probability 0.95. Again, this is probably conservative because this bound is only reached when theta is close to 0.5. In our example, theta is 0.05. So the confidence interval could be narrower. But since we don't know that, maybe in New York City, there could be half of the people that have COVID-19. We want to make sure that the confidence interval is valid, no matter what the estimate is. Of course, you can make it, you could do the same trick that we did with the sample mean and use the actual fraction of positive cases to make the confidence interval narrower. But anyways, let's not get into that. Okay, so now let's apply our result for general probabilities to the population proportion. As I have said, in that case, when we have this data, our random samples correspond to Bernoulli random variables, because if we select a certain person, if they have COVID-19, then the random variable is going to be equal to 1. What's the probability of that happening? Exactly the population proportion of people that have COVID-19 in New York City. So these guys are Bernoulli with this parameter. So we can directly apply the previous result and have this confidence interval. If we're interested in a 0.95 confidence interval, this is the confidence interval that we can apply. For example, we could use this confidence interval to decide what n should be so we get a certain accuracy in our estimate of the prevalence, which is probably what you should do before going out and sampling a number of people from the population. So if we want to estimate the prevalence and we want an error of less than 1% with probability of around 0.95, then what we should do is make sure that this is smaller or equal to 1%, right? The 0.95 probability is going to be guaranteed by the fact that this is a conservative 0.95 confidence interval. So setting 0.98 smaller than divided by square root of n smaller than 1%, we get that we need at least 9,000 measurements, which is very, very small given that the whole population is 8.8 million. Okay, so this is kind of nice. Of course, if we used a better estimate of the prevalence, then we would get a narrower confidence interval, but we don't know the prevalence. Okay, so hopefully that makes sense. And this is an important application of confidence intervals for proportions, just determining how many samples you should actually obtain. Let's take a look at an application of our confidence intervals for probabilities to the Monte Carlo method. Remember that what do we do when we apply Monte Carlo simulations? We want to estimate a certain probability, and the way we estimate is by simulating the corresponding outcomes and seeing when the event of interest happens. And that fraction is going to be the fraction of times that the event happens is our estimate of the probability. The key question often is, have we done enough simulations to get a sufficiently accurate probability? Because obviously we cannot do infinite simulations. We can use confidence intervals to make sure that that is the case. So let's take a look at an example. This example is from the example that we used to illustrate the Monte Carlo method quite a while ago, but you can go and check out that video if you don't remember. Basically, we're trying to predict the outcome of the Tokyo Olympics, in particular the 3x3 basketball tournament, which involved Belgium, China, Japan, and some other countries, and we want the probability that a team wins the whole tournament. Basically, what we did is we came up with a reasonable way of estimating the probability that each team beats every other team based on the quality of their players, because we have ranking points for each of the players. And then with those probabilities, we can just simulate the whole tournament. Okay, there was a previous stage that I'm not showing you here. And then there was this, depending on how you ended in the preliminary stage, then you were put in this playoff bracket that ended up with the final. Okay, and whoever won the final won the gold medal. Okay, so we can actually simulate under the assumptions that our estimated probabilities for the head-to-head encounters are accurate. We can estimate the whole tournament many, many times, and the fraction of times a team wins is a reasonable estimate for the probability that they will win the whole tournament. So we do that. We simulate the tournament n times independently, and in each we know that in each simulation the probability that the team wins is equal to this underlying probability of the event that team wins, right? So we're exactly in that case where we have Bernoulli random variables, where each simulation, imagine we want the probability that Serbia wins. Well, what's the probability that they win in the simulation if our assumptions on the underlying probabilities are correct? It's exactly the probability we're after, right? The probability that Serbia wins. So we compute the fraction of times that Serbia wins in the simulations, and that gives us the estimate of the probability. This is exactly within, this satisfies the
assumptions of our confidence interval for Bernoulli random variables, and in fact, it satisfies them often better than when we obtain observational data, because here we can guarantee independence, which is much more difficult to guarantee when we're actually gathering data in practice. So the Monte Carlo method is kind of the ideal application for confidence intervals in that sense. So now we can build these confidence intervals that we have for probabilities, where we get 0.5 from this bound on the variance, on the standard deviation rather, okay? And if we're interested in 0.95 confidence intervals, then this constant is just equal to 1.96. So we have our confidence interval for our Monte Carlo probability, and now we're going to apply it to our estimate of who is going to win, well, who won the Summer Olympics. Of course, we were doing this after the fact. After 1,000 simulations, it turns out that Latvia seems to win more often. So should we trust this result? Have we done enough simulations? Well, we have to take a look at the confidence intervals, right? In this case, the confidence intervals overlap. The probability that these two teams win was relatively close, right? So he realized that here we're within 0.38 to 0.46. So it's actually so close that there is significant overlap between the confidence intervals. Here we cannot really be sure that Latvia actually wins more often. This might just be noise, as indicated by the overlapping of the confidence intervals. So what do? We do 100,000 simulations, and now we compute the confidence intervals again. It turns out that in this case, Serbia wins more often, which backs up my my statement a moment ago that maybe Latvia was winning more just because of noise, because we have done limited simulations. Have we done enough simulations? Well, let's take a look at the confidence intervals. In this case, the confidence intervals are non-overlapping, indicating that it's quite likely that Serbia actually has a higher probability than Latvia. Okay. This is how Monte Carlo. This is how we use confidence intervals to ensure that we have performed enough Monte Carlo simulations. In fact, in the tournament, Serbia lost in the semifinals and Latvia ended up winning, in case you're curious. Okay, let's take a look at an application of confidence intervals to a real poll in the previous presidential election, which was Trump against Biden. This poll was in Pennsylvania, which turned out to be quite important for the actual election. In the poll, 281 people voted for Trump and 300 said they would intend to vote for Trump, and 300 people said that they would vote for Biden. So we're going to apply confidence intervals to this situation, where the parameter is the fraction of Trump voters in the population. Okay, so theta here indicates the number of people in Pennsylvania, the fraction of people in Pennsylvania that intend to vote for Trump. We built a confidence interval because basically this is exactly the case where we're trying to estimate a population proportion, so we can just apply that result and we get this confidence interval. Here, we're making assumptions that are completely wrong, right? Because it's very likely that this poll did not consist of people randomly sampled from the Pennsylvania population, okay? But, for the purpose of just this video, we're going to assume that were the case, okay? In that case, this would be a valid confidence interval. And now we can replace n by 581 because that's the number of samples in our data. And we get this confidence interval that is equal to 0.444, that is between 0.4 and 0.524, okay? So now we have to think, if we're predicting the outcome of the election, essentially what we want is the probability that Trump wins in Pennsylvania so that we can combine it with the probabilities that he wins in other places and come up with an estimate of what is the probability that he actually wins the whole election in the United States. So What is the probability that Trump wins according to our confidence interval? I would like you to think about this, like if necessary, pause the video. What I'm asking you is the probability that this parameter theta is greater than 0.5. So the answer, according to the confidence interval, is that we have no idea. Why? Because in our framework that we're applying to compute confidence intervals, we're modeling this parameter as being deterministic. We're in a frequentist framework where the population parameter is deterministic. All we can say is that we're not very sure, like it's very possible that Trump would win in Pennsylvania because 95% of the time the population proportion ends up in this interval, and that interval contains 0.5. This is a very weak statement that would not help us very much in the estimate of the actual election. In contrast, if we apply a Bayesian point of view here and we say that this guy is actually a random variable and that we have certain uncertainty associated to it, then we can come up with statements such as the probability that Trump wins in Pennsylvania is whatever it is. We covered this in our video on Bayesian models, but you have to remember that the actual probability that Trump would, the probability that Trump would win would be this one, completely depends on our prior distribution assigned to the population parameter. So in this other framework, in this Bayesian framework, we are forced to come up with some prior distribution of the parameter. This is in contrast to our frequentist framework for confidence intervals, where we don't need to do that. The good news is that if we're doing something like estimating an election where we need these probabilities, then the Bayesian framework gives you these probabilities. The bad news is that these probabilities are going to depend on the prior, which is a problem that we don't have with confidence intervals. Here we have changed the prior and the probability completely changes. Okay, so there's no free lunch here, and which framework is appropriate is going to depend on the specific application. Okay, just to end, let's go back to the assumptions that underlie our construction of confidence intervals in order to illustrate the importance of satisfying those assumptions. We're going to look at the problem of estimating the fraction of time that it rains in Coos Bay over a year. We have the ground truth data, which tells us that fraction of time is 11.3%. But we want to estimate this from 500 hourly measurements. Okay, that's our goal. So now we build a confidence interval where we're going to take those 500 hourly measurements. We're going to take the fraction of time that it rains in those 500 measurements, and we're going to apply our confidence interval. Here, this is just a sample proportion, right? Or equivalently, like these are Bernoulli random variables, each hourly measurement, so we can apply our confidence interval for proportions and probabilities. Okay, so now imagine that what you do is you say, okay, I'm going to just pick some random time during the year, whatever it is, and I'm going to average the following 500 hours, like whether it rains or not. I want you to again pause the video and think whether this makes sense, like if we're going to get good confidence intervals on our parameter of interest. So let's take a look. The confidence intervals are not great. In particular, most of them don't contain the parameter of interest. So what is going on here? Well, what is going on is that we're violating the independence assumptions. We're sampling things sequentially, and these measurements are highly correlated. When we measure in the summer, it doesn't rain. So the fraction of times that we observe rain in our data is smaller than the true population fraction of rain, the true population probability of rain. When we sample in the winter, sometimes it just rains a lot. So then that pushes the average up because we have this dependence within our measurements. So, where do things break down in our original assumptions? Well, it's that independence assumption. If we actually do randomized measurements where each measurement is picked randomly from the whole year, then we break this temporal structure and we get very good confidence intervals. In fact, they're overly conservative because we have applied these confidence intervals that estimate the standard deviation using this bound on the probabilities, and we could make them narrower. So that's why, in case you're wondering why they really all contain the parameter. Okay, so this showcases that it's absolutely critical that the assumptions of independence and uniform sampling in the population are satisfied. Of course, this example is a little bit idiotic, right? It's kind of common sense. You want to estimate the fraction of time it rains over the whole year and you just take measurements in March. That makes no sense. But it's very easy to make similar mistakes in other situations where it's not so obvious that you're violating independence assumptions. All right, so what have we learned? We have learned how to build confidence intervals for proportions and probabilities. We have learned how to apply confidence intervals to know whether we have performed enough Monte Carlo simulations to obtain an accurate estimate of a probability. And we have talked about the limitations of the confidence interval framework in the sense that it doesn't really give you a probability as in the Bayesian framework, but we have also noted that in the Bayesian framework, then you have this prior that influences the probabilities that come out in your results. And also we have seen that the underlying assumptions of independence and uniform sampling are critical for confidence intervals to actually be real confidence intervals. And that's all I got. Thank you very much.